Okay, good morning, everyone. Today we are going to learn about the relational algebra operations of MapReduce. Okay, I think you can hear me properly. We are going to learn. Today's objective is very simple one, that we are going to learn about relational algebra operations using MapReduce on database systems. Okay, so I just want to show you like what all things are done till now. Can you see this screen?
Yes, ma'am.
Yeah. Okay. So this is the syllabus that I'm showing you right now. In the syllabus, there like we are going to complete first two chapters of the syllabus today. Okay, that's why I want to show you that how much topics are over. We have learned about big data and Hadoop. What is big data? Characteristics, types of big data. Then traditional approach and big data approach. Then some case studies. Then concept of Hadoop. What is mean by Hadoop and core components and the ecosystem components of Hadoop. Okay, so on this topic, around 20 marks of paper is there. Minimum 20 marks of paper is there. 10 marks is there for the big data kind of problems, and 10 marks on this ecosystem and core component. Core components which means HDFS and MapReduce ka basics are there, and in core components again Hadoop ka goals are there. Hadoop ka goals, assumptions, then how Hadoop is going to solve this big data problems. So all kind of questions are there in this particular topic. So around on this particular first chapter, there are 20 marks of questions which are asked in the paper. Okay, so the first part of this particular chapter is about big data, and the second part is about the Hadoop ka basics. In the first part, we learn about big data and comparison with traditional system and case study. And the second part, we study about the core components of Hadoop, means the four components, that common library, HDFS, MapReduce, and YARN. So there can be a question to explain all four components, or select any two components and explain them in detail, or HDFS in detail, or only MapReduce in detail. An ecosystem contains the diagram where all the some of the important ecosystem components are there as per the scope of the syllabus. Okay, and you just have to draw the diagram of ecosystem is what are the advanced components on the top of core component, which help us in doing the analytics. So there can be a question on ecosystem or HDFS or MapReduce in detail with the help of an example. So like this is done. Okay, first chapter is, it is very important to learn the first chapter, because around 20 marks of paper is matlab, every paper is having at least 20 marks of questions on this particular chapter. Then we have studied about the second chapter. Second chapter may we have studied, I have taken one lecture on distributed file systems, like why this distributed file systems, what are the problems, what is vertical scaling, horizontal scaling. And then we studied MapReduce algorithms or MapReduce programming, where what how to, here in the first chapter we concentrate on job tracker and task tracker kind of component, and here we mainly concentrate on mapper and reducer ka job. Okay, so and what is combiner, what is the use of combiner, what is the shuffler task. So all these things we study in this particular 2.2 of your syllabus. Then in 2.3 the algorithms are there. So we have gone through these algorithms in the last lecture. Matrix multiplication we have done. Before that I taught you about matrix vector multiplication. Matrix, so algorithms here means that word count algorithm, matrix vector algorithm, matrix to matrix multiplication algorithm, one step and two step. And then there is something called as a small topic is there in the syllabus. Okay, that is a relational algebra operations, computing selections or projections or union intersection difference by MapReduce. So it is a very small topic of the syllabus. So today's objective is just to cover this particular topic. Okay, so it is not a very heavy lecture for today. So you just understand it's a small kind of lecture where we are learning what are the operations which are possible and how they are to be done using MapReduce. And then we'll see what are the limitations. So we will complete first two chapters, and in tomorrow's lecture I'll start with NoSQL databases. Okay, so I think you have understood that we are learning this particular small topic of your syllabus, that is relational algebra operations, yeah, or union intersection, how it is to be done, and what are the questions which are asked in the university paper. So for this particular topic in the university, they ask the questions on only 5 marks. So the total weightage for this particular today's lecture is 5 marks question that is asked in around alternate papers. Okay, so I even I want to show you about my COs, because always we are as a NBA procedure and NAC procedure, it is mentioned that the student should know what are the course objectives and course outcomes. So like every teacher prepares a file in the beginning of the semester where we prepare the lecture plan and we decide about the course outcomes. So these just I want to show you what are the things which I am going to trying to what are my objectives and what I want at the end of this particular year when you study big data. So these are my 6 course outcomes, where I'm saying that in the first outcome, my students will be able to learn about, will be able to understand about the key issues of big data and what are the associated applications. So for this particular to achieve this, this is I'm mapping this to the first chapter ka big data part. Okay, this my CO is mapped to the first chapter of your syllabus ka big data part. And my target is that you need to understand what is big data and what are the case studies in the real world about big data. Okay, so what you do is that today or tomorrow I am going to post one assignment of case study of big data, which normally you have to attach into the journal. So it is a part of the term work. So you can finish that in 1 week of time. And in the second chapter, so first and second COs ka is done. Uh, at the end of the today's lecture, we are done with these 2 COs. In the second CO, I'm saying that my students will be able to develop the problem solving and critical thinking skills in fundamental enabling techniques like Hadoop and MapReduce. So my students will be able to solve the problems. So we are going to see the problems such as word count, matrix multiplication, and relational algebra operations by using Hadoop and MapReduce in the big data. Okay, that is the second. Third objective is about NoSQL databases that collect, manage, store, query, analyze. Okay, and these 3 are for the advanced topics. Here, fourth is about the business models and applying the tools. Uh, and the fifth one is about the applications such as social media application, recommender system, and page ranking algorithm. And the sixth one is mapped to the mini project. Okay, and so what this last 3, so I'll explain you while I'm going to teach you. You can concentrate on sixth one. Sixth one is about solving the real world problem, and it is at the application level. Like see whenever we are teaching, that time we are following that Bloom's taxonomy. Bloom's taxonomy means there are multiple levels of understanding of a particular topic. So here the level of understanding is just to understand. Understand is the very basic level, and then you analyze is the second step. Then analyze is fourth number. Application, analyze, and then at the end, whenever you do the research, it is at the top level. Okay, so this is at some high level learning. The sixth CO is some high level learning where I'm saying that my students will be able to solve complex real world problems. So identify a group and you have to do the mini project. Your mini project will be any application which is recommender application or social media application or health, medical, or any particular domain. May you are doing some analytics using some big data tools. And here we are learning about tools in the fourth, where actually introduction of tools is done in the ecosystem, and the tools are Hive, big kind of tools. Okay, I think, is it confusing? I think you should be able to understand. We have done with what I told you just now is that we have done with the big data and Hadoop ka basics part, and then HDFS MapReduce. For that, my course outcomes, means my objectives are that my students will be able to know about big data, and they will be able to know the basic programming skills of Hadoop. And here in the last you, I'm saying that they will be able to solve the real world problem. So this will not happen at the end. If you start, you have to start working from now for the CO6, where my objective is that my student should be able to solve a real world problem use of big data analytics. So here you start working from now. You make the groups. I suggest you that you make the groups which are there already, your BE project groups, and you submit the topic. Okay, I'll share the Excel, and I'll share the assignment for the first CO about big data case study. And you start. You can select the same case study, and you can implement your project for that case study. And the project can be a recommender system, or it can be a social media application of graph kind of application by using Neo4j tool, or NoSQL, or it can be using any tool of the Hadoop ecosystem. Okay, what are the tools of Hadoop ecosystem? That Hive, Pig, PySpark, all these are the tools. So you select any one particular technology. Hive is easy to do, and using that you have to do this mini project. Okay, so this was about this. This is the list of experiments. Please go through the list of experiments, and now you start working for this practicals. The first step is that here the study and installation of Hadoop first experiment. So you can install it on Windows. It is not a problem, and you get a prompt. You get a prompt of Hadoop, and in front of the prompt you can perform some HDFS ka commands. Okay, so study and installation and this HDFS ka commands ka execution is the first job. Then you write for this third and fourth and sixth experiment. You can use a Python language. Okay, are you understanding? I'm just talking about the course, big data course, how we are going to handle the course, because today's topic is very light, so I can give you the background about the subject, how we are going for this subject in the semester. There is the experiment 3, 4, and 6. This you have to do by using Python or PySpark. So for that you will have to install Hadoop, and then you will have to install PySpark. So you can use only Python or you can use PySpark. Okay, but what we are doing now, we are not in the college, so we are not going to have the entire cluster like the proper cluster which we study theoretically. Here we will install the single node installation of PySpark, and we'll see the execution of this particular problems using MapReduce. Your program is in the form of mapper and reducer, but it is executing on the same machine. Okay, if you want to really do proper kind of experiments, then what you can do is that in your Windows or your Linux, if you are having Linux operating system, that's good. In the Linux operating system, you create a virtual machine. In the virtual machine, you install. You should have a Ubuntu operating system. In the Ubuntu operating system, you will have to in your virtual machine ka Ubuntu machine mein, you will have to install the Hadoop. Then you will have to install the PySpark, and you may have 2 3 virtual machines, and you can have the cluster created. Or if it is a single node cluster installation, then on that virtual machine you install the single node installation of Hadoop. So it is a only one machine which is acting as a master and slave, and then you can configure that Hadoop with Eclipse, and then you perform the practicals using Java or Python with Eclipse. Okay, and the first 3 experiments are word count, implementation, sorting a list of numbers, and matrix vector multiplication. Okay, another way to perform these practicals is about Cloud Era. Cloud Era. So Cloud Era is a website which gives you the runtime environment. It gives you runtime environment for all the Hadoop ecosystem components. So it will allow you to use Hive, it will allow you to use Pig, it will allow you to use Scoop to transfer your relational database into the Hadoop HDFS format. So this Cloud Era will give you the entire cluster, plus it will give you all the facilities of the Hadoop ecosystem components. Okay, so you can go to the Cloudera website, and if your machine is a good machine, laptop with at least 4 GB memory, then you can download and install that Cloudera client. So it is like a cloud on cloud. We are performing all these practicals. That is also the best method. So I suggest you that you can also try that also you can try. This is also easy. Like here you get, if you install Hadoop and HDFS, you get a prompt, and in like जैसे Python में prompt आता है. वैसे you get a prompt, and in front of the prompt you are executing your program. So it is also easy method. But Cloudera will give you it is an integrated development tool on cloud with all the Hadoop ecosystem components. So Hive has Mapeak hai or Scoop hai, all the tools are there. PySpark will be there, and then you select a particular tool and you can execute the program. So if your machine is having 4 GB, if it is better, if it is greater than 4 GB, then you can download the Cloudera client, and you can execute your experiments. Okay, so as I think this month we are working like this only online. So it's better you start working for this program. So actually, when you do this kind of programming, you get a clear picture about the subject. Okay, so we have discussed enough about it, that the syllabus and the practicals. Okay, so we will complete the second chapter today. So is this screen is visible to you now? PowerPoint.
Yes, ma'am.
Hmm.
Um,
Okay.
the syllabus is still visible.
No, I want to show you the PowerPoint, my presentation. This presentation, is this visible now? Because I'm not seeing that prompt. वो hide हो गया अभी. You are presenting वाला एक आता है ना prompt, that is not visible right now. So is this
No,
visible
ma'am.
to you? हाँ.
No, it's still
You.
on the syllabus.
अच्छा. Okay, then I have to change. Here. Okay. Uh, so uh, so we are going
Yes.
to. Yeah. I got the message. Now, so what we are going to do is that we are going to see the relational algebra operations using MapReduce today. Okay, so we'll have like this is the structure of our MapReduce, where in the MapReduce layer we are having two processes running on the master node and slave node. On the master node, the process is a job tracker. Maybe Sela, you must have by hearted this because I'm telling this in each and every lecture, but others I don't know. That's why I'm just repeating this thing so that there will be a link in the lecture. Okay, so in the high level architecture of Hadoop, we are having two important basic components, HDFS and MapReduce. HDFS is responsible for distributed storage of the data, and MapReduce is responsible for performing mapper and reducer tasks. So, and it provides the software framework which help us to do the parallel processing. Okay, so in case of big data application, always remember there are two steps. First step is to store the big data, second step is to process the data. In the first step, HDFS layer help us, and we can store our data. For example, here matrix M is stored in the form of three elements: row, column, and the actual element ka value. And now I'm talking about relational algebra. So if it is a relational algebra, then my database ka table is represented as a relation. So it will be a relation R, and this a particular element is the row of the table, where every column is an attribute. Okay, so my table, relational table, is also stored in the form of a distributed fashion in the form of a file into HDFS. And how it is stored? It is a relation R. Relation R indicates the name of the table, and inside the bracket I'm going to have some attributes. These attributes are nothing but the column ka values. Okay, so it will be R, and in the bracket a list of values. In that format, a particular record of your table will get stored. Okay, so in case of Hadoop, we are having these two main components, HDFS and MapReduce. HDFS is responsible for storing the data in a distributed fashion on data nodes, and name node is a master, data nodes are the slaves. Actual data is stored on the data node. And in case of relational algebra, your table is a relation capital R with a set of elements, and the elements indicates the attributes of the table, that means the columns of the table. Okay, this way the data will get stored. Now the MapReduce is responsible for distributed processing. It will give you the software framework that will help us to write the program, because it will produce the APIs, application programming interface library functions. And we can use that library functions directly in our Java program or Python program. And we can write the program. So programmer's job is not that tough. The architecture, like the person who has developed this Hadoop, they are so intelligent, and their job was complicated to write down all these components and working of these components in coordination with each other. So it's a big job, and they have made us our life very simple. We just have to use these APIs provided by MapReduce, and we just have to write the program and submit it to the Hadoop architecture, and everything will be done by Hadoop. Okay, so this MapReduce layer is having two, it is also master slave architecture. It is having two components, job tracker running on master and task trackers running on every slave nodes. Okay, so mapper your entire job is submitted to the job tracker. It will identify the mappers, and it will identify the task trackers, and it will send this task of mapper and reducer to different task tracker to execute it. Okay, and there is a shuffling task which will be done by the Hadoop framework. Okay, this is the background that you need to know in order to understand the today's lecture. Okay, so in case of this relational algebra, okay, we'll see the questions which are asked on this particular topic in the exam. Okay, so I'm not going into the details, because each and every topic of this big data is such a complex problem, or we can go in multiple depth. Like one particular topic can become one subject. So it's not possible to study each and every topic in that depth. Okay, so I'm that's why I'm referring the university question papers for each and every topic. Otherwise, on the net, I'll see that there will be one particular course for one particular topic, and so we cannot we are going to cover so many small topics in a big data subject to give the proper overview of this particular analytics. So that's why I'm referring the paper, and depending on the weightage and depending on the questions which are asked in the exam, and depending on your textbook information, I'm preparing the slides. Okay, so for this MapReduce relational algebra, there are always only these questions are asked. MapReduce implementation of join of two relations with an example. So you have to give one real world example and explain how to join two different tables. Okay, relation means the table, database ka table, and how to join two tables by using one example. And this and both the things are asked for 10 marks. So this particular topic is for 5 marks. Then there is one more question asked, that MapReduce algorithm for natural joins. That is for 5 marks. And MapReduce algorithm to perform intersection of two sets is also for 5 marks. So on an average, 5 marks is the weightage for this particular today's lecture topic. Okay. So let's see. So this is the question which is asked in the exam. Explain MapReduce join for two relations with an example. Okay, so have you understood what we are going to learn today? We are going to learn today about the relational algebra operations and intersection and union in detail. Okay, so here suppose you want to fire a query on the database, like what is the bank balance of a particular account holder. So this is not a suitable query of MapReduce. Here you need to search through such a long big data, like such a big data, and you have to find out the bank balance of an account. This query cannot be a big data query. Okay, because the searching will take lots of time. So it is not suitable, but it is suitable for some other kind of activities. Like suppose you want to count the number of friends of a user on a social networking site, like on Facebook, you want to find out that how many friends are there. for a particular user. Whenever you visit the site, you see the total number of friends for your account. Or suppose you want to visit to your friend's profile, then you will be able to see that what are the common friends uh, between these two users. So such for such kind of queries, we are going to select the MapReduce operation to perform. And for a database table, we assume it as a relation, and it is table is having the columns as attributes. So relation can be shown in the form, and we use these terms relation, tuple, and schema. So relation is actually the table of your database. Tuple is the row of the table, and it is represented like this: R in the bracket, attribute 1, 2, 3 up to n, and the set of attributes indicates the schema of your table. So here this will be the name of the table when you store the information in the distributed fashion. This will be the name of the table, and these are the values. Maybe key value pair, or it will be the value. So this way the data will be stored. So relation, however big, it can be stored in a distributed file system. Because they don't fit on a single machine, they can be broken into pieces like HDFS, and they are stored in a file system. So this is actually your file, similar to a text file where your data is stored. Okay, but we can perform these operations on this data. What are the operations? Relational algebra operations: selection, like select query kind of operations, then projection of your table in database ka table in some particular other format, then union of two tables where we are learning about joins. So your join ka question belongs to this union part, like joining two tables on the basis of a foreign key or common key between these two tables, joining part. And then intersection is what are the common attributes in two tables, what is the difference between the table or natural join or grouping or aggregation. Okay, so such kind of operations you can perform using relational algebra. Okay, so let's summarize this. What I'm trying to tell you in this particular slide is that you can store your data or table of your database systems in the form of a file onto the distributed file system, and your entire database can be divided into multiple chunks. And how it is stored? It is stored in the form of a relation. So in that relation ka key value pair, your R indicates your name of the table, and inside the value you have a list of values or list of attributes. This list of attributes are nothing but the value of the column of your table for that particular record. So this one relation indicates one row. Okay, unless you understand this properly, you will not be able to understand the algorithm. Okay, so let's see this. The a particular row of your database ka table is stored in the form of such tuple, which is a relation, and the value is the list of attributes. Okay, so R and a list of attributes, where R indicates the name of the table and attributes indicates all the column ka values for this particular record or particular row. So like this, if there are millions of rows, millions of these relations are stored, and so a chunk of relations are stored on a particular data node. Okay, this way your data is stored, so you should know this. And what are the operations we can perform in relational algebra? That select query or projection of your table in a particular format, or joining of two tables, or intersection of two tables, or difference or natural join, or grouping and aggregation. And in the exam, they are frequently asking about union and intersection. So by referring the textbook and by referring the papers, we are going to learn about union and intersection today. Okay, so for selection, you can see this diagram. Like suppose this is your relation R1, R2, R3. Like every row, there are 5 rows in the table, and all the 5 rows are shown here. So in this case, like here, what we are doing is that we are trying to do the analysis for a structured data. We are trying to do the analysis because big data analytics may your data can be of any of the type. It can be structured, unstructured, or semi-structured. So if it is a structured data, and if you want to do some kind of analysis on that, because the analysis query is a query such that for the Facebook, you want to find out that in between two users, what are the common friends. Okay, such query, this what I want, like here grouping and aggregation may. I've taken this example to explain you about intersection. So what I'm saying here is that so the example for that particular relational algebra operation is that count the number of friends or users, count the common friends. Okay, that is the proper example. Like suppose for a social networking website, we want to find out what are the common friends in between two users. Then such query is not possible using the normal way of doing analytics because the size of the data is huge. So in that case, MapReduce is suitable. So in that case, MapReduce is performing your big data ka type is a structured data. Big data can be a structured data, unstructured data, or semi-structured data. Now, in the next chapter in NoSQL databases, we are going to see that how unstructured data is to be analyzed or how semi-structured data is to be analyzed. What are the different databases, NoSQL, not only SQL databases. So that we are going to study. But here, for this particular topic of MapReduce, we are concentrating on the structured data, means your database. Okay, because we want to fire the query like analytics kind of query. So here the relation indicates the row of your table. This relation indicates the row of your table, one row. So there are 5 rows assumed. So that's why all the attributes are same. Like here it is a rectangle, then square, a circle. Okay. So selection query is just depending on a condition. So apply a condition C on the each tuple. So it is very simple. You just apply some condition on a relation. So on the tuple of a relation. This is a tuple. R1 is a tuple of relation R, where R indicates the name of your table. So apply the condition on this R and produce some output if the condition is fulfilled. So if the condition is satisfied, all of this out of this 5, we are getting two records, relation R1 and relation R3. So selection is a select query similar to the database. So it's very simple to understand. Okay, so the first operation is about selection where you select the particular tuple who satisfies the condition C. Then for projection, this is your actual database where you are having 4 attributes. And now you want to just project some of the attributes only. So it is applied on the entire table, and you are just projecting only 2 columns of your database. So from this relation, we are just taking only 2 attributes which are mentioned in your query. Okay, so this way it will do. So you should know like what is this R. This is a particular row of your table. Okay, and it is stored like so we can say that R1 and R2 is stored on data node 1, R3, R4 on data node 2, and R5 on data node 3. So there are 3 different data nodes. And the mapper is going to be executed, which will extract only these 2 attributes, which will be given to the reducer, which will show the output. This way it will work because MapReduce, I told you. I'll just repeat this again for MapReduce that in case of MapReduce, when you write the programmer is going to write the mapper function and reducer function. Mapper ka input is key value pair. Mapper ka output is intermediate key value pair. That intermediate key value pair is sorted by or shuffled by the shuffler of the framework, and depending on the key that will reach to the reducer. The output of shuffler is key and list of values that is input to the reducer, and reducer is operating on that list of values. Okay, so have you understood that what I just now said? Input, there are 3 functions: mapper, reducer, and shuffler. Mapper ka input is key value, mapper ka output is intermediate key value, intermediate key value is input to shuffler, shuffler ka output is key and list of values, and then reducer ka input is key and list of values, that is the output of shuffler, and output of reducer is some summation done on the list or some aggregation operation done on the list of values. So it is again a key value pair. So we get the answer, our input is in key value pair and output is also in key value pair. So here our key is can be R and the value is this 4 elements. Okay, for this particular row, key is R, capital R, and value is equal to these 4 elements combined together. That will be the that is going to represent your database ka row. Okay, that is in the key value pair given as input to the mapper, and mapper will just select two attributes and it will send it, and that will be stored in the form of a key value intermediate key value pair. Shuffler will shuffle the same keys on particular table or depending on the logic selection में कुछ complication नहीं है, reducer don't have to do much work. Okay, so we are this now we are going for the this question answer for this question. MapReduce join of two relations. So I'm taking an example in your database. Suppose you are having two tables. Normally, whenever you are doing any application of e-commerce website or some shopping or buying, what we do is that we have a customer table and transaction table. We don't have a single table where everything is stored. We have a customer table dedicated to customer where information about all the customers are stored. Customer ID, his name, his address, phone number. And transaction table may we keep the transaction. So we normally keep two separate tables. One table for customer, one table for transaction. And in the transaction may primary key is a transaction ID, and in the customer the primary key is a customer ID. And in the transaction table may you have a foreign key as a customer ID. So both the tables can be joined with the help of a foreign key customer ID, which is a primary key for the customer table and foreign key for the transaction table. Okay, now suppose you want to find out some analytical reports on this particular transaction about a customer. Then we can perform a join operation on this separate tables using the common column that can be the customer ID. Okay, to get some analytic reports. So here for this particular example, you just keep in mind as example of a customer and transaction where customer ID is a foreign key and both the tables can be joined using that customer ID to do some kind of analytics or to solve some kind of query. Okay, so now in case of MapReduce, there are two types of joins. The joining operation can be performed by two ways. One way is map set join, like the join is done at the mapper location, or there is another method, like we can perform this join operation at the reducer side. Okay, so just remember there are two types, or there are two methods using which we can perform the join operation on two relations. The first method is about a map side join, and the second method is about the reducer side join. So mapper side join means at the mapper side only we perform the join operation and we just short shuffle and show the output. But in reducer join, the join operation is done by the shuffler. So here reducer is not, and it is done at the reducer side. So mostly it is done at the reducer side, but shuffler is going to help in that case. Okay, so there are some pros and cons in this both the methods. What are they is that in case of map side join, mapper performs the join. So it is mandatory that the input to each map is partitioned and sorted according to the keys. So some more like mapper is working hard. Mapper is working very hard in this case because everything is done at the mapper side, and then simple shuffling and reducing is done afterwards. And you do your main job in map, and here in reducer side join me you do the main job of joining at reducer side. So here what is the advantage of map is that it is very fast. It is very fast because mapper may locally something is done and then mapping and reducing is happening in the distributed architecture. Okay. Now you should remember I'm assuming that all of you have gone through the mapper and reducer ka slides and you are thorough with the working of mapper and reducer with respect to at least word count problem or any matrix multiplication ka problem. Then only you will be able to understand today's lecture. So what I'm saying is that here the mapper and reducers are running at different data nodes or by job trackers of that machine, task tracker of that task tracker of that machine. So what is happening here is that if we have to perform joins in MapReduce, there are two types of joining, two types of techniques. By using the first technique, you do the joining kind of logic in the mapper location or at the reducer location as a second method. So in the first method, what is the advantage of the first method is that it is very fast because locally mapper ka machine may something is executed or some logic is happening or execution is happening uh, locally, and then in the distributed network everything is happening, shuffling and reducing and mapping. So it is fast. but it has lots of constraint. Like if your both the tables are too big to fit into the memory of a single machine, then this method is not possible. Okay, we'll see with the help of diagrams afterwards. But right now we can say that mapper side join is fast and reducer side join is flexible, but it is very slow. But if your both the tables are very big, too big to fit into the memory, then you will have to use reducer side join. If one of the table is small, then you can go for the first method. Okay. So I think so here you don't try to, you will not understand anything. You can understand only right now. Even if you understand these many things, that is okay for me. Like if whenever you are performing any SQL kind of join, there are two techniques to do this joining operations. One technique may mapper side में joining का logic will be executed. In another technique, reducer is responsible for performing join operation. The first method is fast, mapper side join is fast, reducer side join is slow. Map side join में there are constraints like one of the table should be very small to fit into the memory. Then it is possible. But here in case of this reducer side join, it is flexible. Both the tables are big data. Okay, and this reducer side join is very simple and easy to implement. Writing this so using second method is simple compared to the first method. Why? Because your most of the sorting operation is done by the shuffler of your framework. And here in this case, in the first method, this that shuffling kind of operation should also be done by this map set join before the actual shuffler. So this is little difficult to write map set join, but reduce set join is simple or easy to implement because the partial job is done by the shuffler of the framework. Okay, so we'll see with the help of example what is meant by that. Okay, so here I'm just showing you right now one example in what is the input and what is the output, and then we will see how it is done. Okay, right now I'm not explaining you that how this reducer and mapper and what is the pseudo code. Right now I'm just telling you about what will be the input and what will be the output for map set join and what will happen. Okay, so here in this example I have got two tables. One table is called one table is the employee ka table, and the another table is a project ka table. So this particular employee, these are the employee numbers and these are the project numbers. So this is a particular project and a particular employee. उसका rate क्या है उसका salary के लिए and how many hours he has worked. So this is about uh, the like monthly basis. This is not an employee table. Only employee का ID is there in this table, and here also only project का ID is there. But in this table, the working hours of the employee, then what is the rate of calculation for the salary is stored. And in the second table, the information about the project is there. Like this is the project ID, this is the project name, and this is the budget of the project. Okay, this is the input. These are two different tables. And what we want is that we want some output the project details. That this is a project one, and this particular name of the project, इसका budget क्या है, and उसका employee and उसका rate. And so we want to combine both the tables. So it is a natural join. We want to combine both the tables. We want all the fields here. So I want the project ID plus employee ID, then the project ka information and the number of hours and rate. So I just want to join these two. And the common key is the project ID here. Here also there is a project ID. Here is also the project ID. So project ID is common in both the tables. On that basis, I want to perform this joining operation using MapReduce. So in case of map set join, this method is suitable because your this first table may be a big table, but the second table may be a small table. Because any organization, the number of projects which are going on will be a limited number of projects. In a particular small one division of office of any enterprise, maybe there are maximum 100 projects are going on. So this particular table is a small table which can be stored into the local memory. All the records can be available inside the local memory. So map set join is more suitable in this case. If both the tables are too big, and then it is not possible. So here the number of projects are less, and this is only the information about the projects. So map set join is suitable in this case. So what happens is that this entire table is there with each mapper. Okay, actually, what here in this diagram, it is, I'm not showing that because it is just an input and output. I just want to explain you. But in the next slide, we will see that how this is happening, where we come to know that this entire table is there at both the mappers. So that small size table is available at the local desk of every mapper. That is the assumption. And only one table is a big table, which is divided into fragments, and that is going to this mapper. Okay, so this some of the records. The first two records are with this mapper. Next two records are with this second mapper. And now this mapper uh, will um, uh, will see depending on the second table ka data. It is going to refer this project one, and it is going to take only this project for the same primary key. It is going to generate the tuple, and then the tuples will be shuffled or sorted by the key reaching to the reducer, and it will show you the output. Okay, so how this is happening is in the next slide. Right now, what you understand from the slide is that you have two tables. One first table is about the project, and the second table is about the project along with the employee with his working hours, and you want to perform the join operation on the basis of the key project 001. And the small table is available with the mapper, which may select some of the row, one particular relation, and it will take the every relation from this chunk of data, and it will do the joining operation on the basis of the key, and it will produce the output. Okay, so so this way it will work. Any doubts in this? Okay, so we are displaying the project details and employee details as output. Okay, so how this is happening here, that in the mapper job is to read the data from join tables and return join key and join value. Okay, so see here the table A and table B. Uh, we are assuming in the database there are two different tables. Table A is going as a to mappers, some mappers, and table B is going to some mappers. Some unsorted data. Mapper is going to do the shuffling and working on that, and then the sorted data. Okay, and something will happen over here. So we'll see that. Let's see what is written here. Mapset join is similar to a join, but all the tasks will be performed by the mapper alone. Only mapper is going to perform everything. So it is mostly suitable for small tables to optimize the task. The map reduced local task will be created before the original task in the cluster. Okay, what is happening here is that a local task on this machine is first created because the second table is available on the hard disk of this mapper. So first some local task is executed on this machine which will be executed, and the output of that local task is taken as input to the actual MapReduce task of the cluster which is happening inside the cluster. So what is written here is important thing. MapReduce local task will be created before the original join uh, MapReduce task, which will read the data from the small table from HDFS and store it in the in-memory hash table. Okay. So we'll see that in the next diagram. What is happening here is that you may have the small data. That small data uh, is stored at the MapReduce local machine, and it performs some task on that, and it generates a text file, hash table file, which is available in the distributed cache of your entire cluster. And then because of this it is available, or it is reaching to each and every mapper. Then this mapper, and this is your second table. Okay, this is your first table, that is a project table, and this is a big table is the table that is used for the salary calculation or the working of the employee. So this small table is accessed by the MapReduce ka local task, which is happening at the locally on that machine. and then it will convert it into the file that will be available into the distributed cache, which will be distributed at different mappers, or will be available at different mappers uh, to refer. And your second table is in the form of a big table. So now every mapper has this small table data and the big table ka chunk of data, and then it is operating on that, and it may perform a map join task here, and then this output is sent into the cluster. Okay, so so it moves the data into the hash table file to distributed cache, which populates these files to each mapper's local disk, and the mapper can load the persistent hash file table back into the memory, and the join is happening at the mapper side. So as I told you, the advantages of map side join is that it is minimizes the cost and improves the performance, because it is very fast, because the joining is done at the locally at the mapper's machine. But disadvantage is that if one of the table is small, then only it is possible. So let's see the next method. Okay, here is the example, another example where I want to fire the query to extract the list of departments in which each employee is working. In the last example, we were trying to find out, we were just joining two tables of project and employee. But here, suppose you are having employee and department ka table. There are two departments and there are multiple employees, and we want to list the departments in which each employee is working. So every employee ka department I want to display the name of the department. So your department ID is a foreign key in this employee table. So one means the development team, and two means the sales team. So I want to display the output as the name of the employee Pranav one comma or sales team. Like this, I want to find out show the output as shown here, that the person name and the department name or team name. So for such kind of query, the department table is small, and so this can be stored locally on every machine. And suppose the chunk is acting as input to the mapper. First two records are for mapper one. It will refer this foreign key, and it will do the joining operation, and it will display the output as the name of the department. Okay, so this is actually the map set join, the example, proper example. So in the exam, you just have to write this and write down the pseudocode. Now the second method is about reduce site join, which is simple to write and fast, because most of the job is done by the shuffler of your Hadoop ka cluster. Okay, so it is the same example. Here in this slide, the same example is there: project table and employee table, and we are assuming that both the tables are big, so we are using this method of reduce set join. So what is happening is that the mapper one is getting the first table ka records, and mapper two is getting second table ka records. So both the tables are the chunk of these tables are input to different mappers. So this mapper is not having the data of both the tables. This mapper is getting data from one of the table and chunk of some of the records of the first table. Mapper 2 is getting some of the records of the second table. So both the tables are at two different mappers. They are not at the same mapper. While in the previous method, this table was small, so by using some techniques, it was brought and stored in the form of HDFS files locally on this machine. And the second table was received by this mapper in the form of a chunk. Okay, and it was performing the job of joining this mapper. But in this method, every mapper is getting different records from different tables. Okay, so what it will do, it will add some tag over here, like here 1 and 0 is added, and from this primary key here, the primary key is the project ID. So what it will do is that will add some tag. So what is the tag used here for this particular table? They are using the tag as 0, the number as 0, and the another table number is 1. So this mapper is here in this case, the mapper's job is just to add the to create a composite key. There was a primary key only in the relation. So it will modify each and every relation. How it will modify? It will convert this primary key into the composite key, And what is a composite key? It is a combination of the primary key and some tag number. And tag number is one for the project ka table, this table, and this tag is zero for the project ka main table. Okay, so it will add that and will create a composite key and the rest of the record. Okay, so this is the output of this mapper one for this these are the keys. So here the key is having project ID and a tag, project ID and a tag, and here it is also having a project ID and a tag, and this tag is different, means this is a different table and this is a different table. Now what shuffler will do? Shuffler will use this data and it will shuffle on the basis of the project key, project ID, uh, um, but uh, but it will shuffle project ID. So project ID is same, and here the project ID is on the basis of the project ID also. It will send that to the different reducers. So the project ID 2 is going to the second reducer. Project all the keys with project ID 1 are reaching to this particular reducer. I'm assuming here there are two reducers. So project 1 ka all the keys will reach to this reducer. Project ID 2, all the keys are reaching to this reducer from this particular mapper output. And from this also project ka ID 1 will reach to this reducer and project 2 will reach to this reducer. So what is the input to this reducer? This reducer is having the project ID with the tag 0 and the entire record, and project ID with tag 1 all the records. And here it is having project ID with 0 all the records for the project 2, and project 2 ka 1 with all the records other. So now what so shuffler has done the shuffling operation. So what is the reducer's job? For it will join this record of tag 0 with all the records of all other records. So it will produce two different rows, like first two rows for project 1, and so it will just perform the join operation. It will remove so this is the input and this is the output generated by this reducer, that with two rows. Okay, so have you understood this? There are two tables. One table is going to one mapper, second table is going to the second mapper. First table ka mapper will just add the tag and it will create the output intermediate key value pair. This will also add the tag to the primary key and it will create the intermediate key value pairs. So these are the intermediate key value pairs. Now these intermediate key value pairs are shuffled by the shuffler of the framework on the basis of the composite key ka primary key, and it will send it to the different reducers. So key with the project ID 1 are going to this mapper, key with the project ID 2 are going to the second reducer, and now it will reducer will do the join operation. What reducer will do? For 0 it will join to the first record, then again for the 0 it will join to the second record. So it will create two records with joining of this rest of the columns shown in the record. Okay, so reducer is performing the join operation, and in the previous case, mapper was doing the joining operation because this entire table was a small table which was available at the mapper's machine, and mapper is used to get, mapper gets the chunk of information which will be joined here, and then it will be shown into the cluster. So cluster mein shuffler don't have to do much job, and even the in the cluster reducer don't have to work much, so it is fast, that map set join. But here the sorting is happening and then joining is done by the reducer. So overall the process takes uh, like more time. So it is slow. But it is suitable and flexible because both the tables can be big tables. Okay, so this is what are the example of your mapper and reducer. Okay, now I think the time is getting over. Okay, so quickly we'll see here in this diagram also, depending on the keys they are shuffled, and we see the results. Okay, so this is what I explained you, and there is another example. I'll share this with you. Okay, I just want to show you this algorithm. Algorithm is that suppose you have two relations R and S, and AB and SC are the sets. Then then you generate the tuple on the basis of the common AB is a tuple of R. So produce the tuple B comma R comma A. Okay, we'll see this properly. In this example, you just want to, there are two tables, customer table and the transactions, and you want to find out that what is the customer name and how much total amount of shopping he has done and what is the frequency of his visit into the cluster. Okay, so the time is is over. I think you have the second lecture, so we will stop now. We'll see the remaining part in the tomorrow's lecture, and then I'll start with. So I'll take 10 minutes to explain you the remaining part, and then we will start with the NoSQL databases tomorrow. Okay, so what we have studied today: relational algebra operations and mapper side join and reducer side join.